about differentiability. Tonight's homework is going to come in the form of Delta Math assignments. There is more analytical work that we can do with differentiability, but I'm not going to be evil and make you try to do that analytical work using the definition of the derivative. So next week we're going to get into analytical rules so that you don't have to do all the definition of derivative. It's very important because it is tested as well, and it's a good, solid, firm understanding of what in the world is going on with this derivative thing and what does it actually mean. And then, but then once we get that, then we'll come back to differentiability. So today's assignment, today's topic is basically concepts, conceptual understanding of what it means to be differentiable and not differentiable. And as I said, we will move on from there. So I'll adjust in terms of everything that's going on. Let's go. So for a function, ftn function, to be differentiable at a point x equals a, f of x and f prime of x must be continuous at x equals a. So the function has to be continuous and the derivative has to be continuous. All right. And of course, you're probably wondering, wait, what does that mean? Well, first off, this has a very important saying that we have in calculus, or something very important, that whenever you hear the word differentiability, you should always be saying in your head, okay, well, differentiability implies continuity. So if, in other words, if a function is not continuous at x equals a, then it cannot be and is not differentiable at x equals a. However, if f of x is continuous, it does not mean it is differentiable. So what I'm trying to say here is that when we talk about differentiability, it's really a two-step check. So whenever you talk about something about being differentiable, at least analytically wise, and you'll see about when we talk about the images, if something is not continuous, it's automatically not differentiable. Okay, so differentiability implies continuity. So if a function isn't continuous, it automatically is not differentiable. However, with that said, just because a function is continuous doesn't mean it is differentiable. We have to check the next part. So if you remember, so it's really a two-step process. So first off, continuity of f of x means that the limit as x the limit, as x approaches a from the left-hand side of f of x is equal to the limit as x approaches a from the right-hand side of f of x, which is equal to f of a. Continuity of f prime of x. So, and what we're saying here is that the left and right meet at a point. Okay, so we talked about that connecting aspect. With the derivative, it's the same thing. The limit as x approaches a from the left-hand side of f prime of x is equal to the limit as x approaches a from the right-hand side of f prime of x, which is equal to f prime of a. And what we're saying here is that the left and right slopes match as we get to x equals a. There has been an AP free response question asking you about the differentiability part and why a function isn't differentiable, and you're utilizing the right-hand side. You could say it in other words. You can say, well, the slope from the left is this value or is this, and the slope from the right is something different. Therefore, you can't look at a graph and think, I'll show you some examples and say, well, the slope is 5 and negative 2. That doesn't make sense. The slope can't be 5 and negative 2. It has to have one slope. So that's an instance where you have something that is not differentiable. However, it could be continuous. Okay.
Mr. G,
yes.
For continuous f, x, and 5, what do you say after when it says right slopes?
Match.
Oh. Thank you.
The slopes match. So I'll work on that handwriting. It's been a while since I've been doing some writing. Okay. So let's look at some examples. Okay. The following are not continuous at x equals a, and therefore also not differentiable. Put not diff. Okay, so these are examples, and you've already seen this. We talked about continuity. So there are three types of functions, or there are three types of instances that are not continuous. The first one is, hey, I don't want you to be all fancy on me. Okay, this is this one right here. This is not, here's a. This one is not continuous at x equals a. Does anybody remember the name for this type of this? This is not continuous, but when we say not continuous, I also want to note that not continuous also means discontinuous. Okay. Does anybody know what this discontinuity is referred to in this picture?
Isn't it two circles at the same point?
No. And the truth is, I don't even know if I verbally stated it. It sounds like I might not have, and that's okay. Sometimes I don't, because I wanted to introduce it right here. So this is an instance where the left-hand limit does not equal the right-hand limit, first off. But the left and right hand both do exist, and this is called a removable discontinuity at x equals a. So that's an example of a removable discontinuity. And since it is not continuous at x equals a, it is not differentiable. So we would say that f of x is not continuous and not differentiable at x equals a. Now, it should be automatic. You know, you can't, if I say not continuous, it's automatically not differentiable. There'll be multiple choice questions where one of the choices might say something like, it is not continuous, but it is differentiable. And you should automatically, well, I don't even have to look at a graph. That is an impossibility, and therefore I can cross that option off. That will happen sometimes on the AP exam. They'll try to do that one like, not continuous, but differentiable. No. Second example. And then I remember what this one is called. Oh, sorry. I made a terrible mistake. This is called a jump discontinuity, and this is called a removable. So sorry if I confused anybody right there. Removable discontinuity. At x equals a. So a removable, also you know there's this one as a whole, but what type of discontinuity is, we call this a removable on the second one. The first one is a jump, and it's kind of like, hey, you're walking along the line, you get closer to A, and then you have to jump over to the next part of A from the left to the right or right to the left. And finally, the last one. You know this as a what?
Vertical asymptote.
It's a vertical asymptote, but in calculus, we often call this an infinite discontinuity. At x equals a. Now there are some other names that calculus books will call them. I think removable. You know, there's other fancier textbooks that in college that might just refer to them as some. I forget. I even forget. I'm taking a calculus class in college right now, and it's like, so like I'm like, why do I have to take? I'm getting a master's so that I can continue to teach. I do not have a degree in mathematics. Is everybody? If you did not know, I do not have a degree in math. I have a degree in finance, actually from MIT. So I'm finishing up a master's degree this year in math education. And one of the requirements, since I really don't have a graduate credit course for calculus, is like, well, you have to take a calculus course. And I'm like, really? And their textbook doesn't call it like infinite discontinuity; it calls it something else. And it's like, but you know, the teacher's like, yeah, I know you know what it means. So I'm actually having to solve limit problems right now. So these are the three examples of functions that are not continuous at x equals a. And if a function is not continuous, it is not differentiable. Now let's look at continuous but not differentiable. Basically, there are three versions of this one as well. Two of them are nearly the same, but there's three of them as well. The first one is something that looks like this. Okay. So that's A. So this function is continuous at A because the left and the right hand sides do meet each other, but this is not continuous, and we refer to this as a corner. Okay. The reason it is not differentiable at x equals a is because the left-hand slope, and I didn't give you any values, but the left-hand slope is positive and the right-hand slope is negative. So at x equals a, the slope on the left does not match the slope on the right, and therefore the slope does not exist at x equals a. Second one, very, very similar. Like I said, these two are pretty much identical. This is called a cusp. But I do want to note that both of these are just, we also, in layman's terms or in easier terms, sharp turns. A function is not differentiable at sharp turns. Can anybody tell me what the difference between these two are, or have an idea of what the differences between 1 and 2 are? Why one is called a corner and one is called a cusp?
The first one has straight lines, and then the second one kind of has curved lines.
Correct. The first one has curved lines, and the second one has, first one has straight lines, and the second one has curved. We call this one has actually what we call concavity, and that means the idea of curvature. Okay, so this one does have concavity involved into it, but that is the answer. And they're both the same reasoning. In the end, the answer for both of them is the same. It's a sharp turn. And if you look at the slope from the left, it does not equal the slope from the right. And finally, the last one, which is the one that probably mixes students up and they don't really believe it, or they might not understand it as well, is something that looks like this. What is this one called? What happens here at x equals a? We need to exaggerate it a little bit more. Let me exaggerate it a little bit more. Oops, change my color back. There's some exaggeration. So what happens here at x equals a? Remember, we're talking about the slopes. What is the slope? Well, this is what we call a vertical tangent. The slope does not exist because technically you could say it's infinity, or you can think of it's negative infinity at that point, and there's not a physical slope there. So while it is continuous, the slope itself does not exist. So on a vertical tangent, if a graph has a vertical tangent, it is not differentiable. And now another graphical property of importance, and this is actually going to come up a little bit more, but there's some homework problems that are going to ask you about this one, so I want to do it and this is what's called a horizontal tangent. Horizontal tangents are very important. This is where, of course, the slope is equal to 0, and it can happen multiple locations. So here, you can say like at 2, here, and like 4, here, and like 6, here, like at 8. You can say that there's multiple horizontal tangents. Horizontal tangents are when the slope is horizontal. The slope is 0. You will see this in some of your examples. I've pushed you pretty hard all week. I really